You ever notice those little mysteries right in your own home? The kind that just make you kind of stop and go, huh? Well, we're about to tackle one that I guarantee you felt before. And trust me, the answer is going to completely change how you see the world around you.
Oh, you know this feeling. It's first thing in the morning, right? You swing your feet out of bed, they hit the nice comfy rug, and everything's fine. But then you take that one step onto the bathroom tile and whoa, it feels like you just stepped on a block of ice. But here's the crazy part. If you took a thermometer to both, they'd read the exact same temperature. So, what on earth is going on?
So the answer, it's not actually about how hot or cold the floor is. It's all about how heat moves. Think of it like a story with three main characters, three secret paths that heat can take. And once you see them, you're going to start seeing them absolutely everywhere. All right, so here's the one big rule you got to remember. Heat is just energy on the move, and it has a one-way ticket. It always flows from something hotter to something colder. No exceptions. So your warm foot on that cool floor, that's a perfect example. The real mystery isn't if the heat is moving, but how it's making that trip. And those three paths I mentioned, well, here they are. First, you've got conduction. That's heat transferred by touch. Then there's convection, which is all about heat moving through a flow, like in air or water. And finally, we have radiation, kind of the mysterious one of the bunch, since it can travel through the total emptiness of space. So let's break these down one by one.
Okay. First up, conduction. This is probably the one you're most familiar with, even if you don't know the name. It's the most direct path heat can take, and it's happening literally anytime two things are physically touching.
Think about a line of dominoes. You just nudge the first one, right? And that energy zips right down the line, domino bumping into domino. But the dominoes themselves don't actually go anywhere. They just pass the energy along. Well, that's pretty much conduction. On a molecular level, the hot, jiggling molecules bump into their neighbors, passing that energy on without the material itself actually moving. And boom, right there, that's the answer to our big question from the beginning. The tile and the carpet are the same temperature, sure, but they have totally different thermal conductivities. That tile is like a heat superhighway. It yanks the warmth out of your foot super fast, which your brain reads as cold. The carpet, on the other hand, is like a heat roadblock. It's a really poor conductor, so it pulls heat away much, much more slowly. So get this, what you're feeling isn't the temperature, it's the speed at which you're losing heat. And this whole conductor versus insulator thing is everywhere you look. Metals like silver and copper, they're amazing conductors. They've got these free electrons that just zip around like tiny little delivery trucks for heat energy. But then you have insulators, things like wood or wool. They're just really bad at conducting heat. And you know, some of the best insulators out there, like styrofoam or the insulation in your walls, they use a really clever trick. They're mostly just air. They're designed to trap air in tiny little pockets, because it turns out that still air is a fantastic insulator. All right, let's move on to our second path. Now with this one, we're not talking about molecules just bumping into their neighbors. No, here the molecules themselves grab the heat and actually go for a ride. This is convection. So the key word here is movement, specifically the movement of a fluid. And, you know, in physics, a fluid isn't just a liquid. It's anything that can flow. So that means liquids and gases. So instead of those stationary dominoes we talked about with conduction, convection is about big groups of molecules moving all together, carrying their heat energy along with them. And this whole process creates something called a convection current. It's a really simple but powerful cycle. See, the fluid near the heat source gets hot. When it gets hot, it expands, becomes less dense, and what does hot air do? It rises. Then cooler, denser fluid sinks down to take its place, gets heated up, and the whole cycle starts over again. It's this simple little engine that drives a ton of stuff in our world, from a pot of boiling water to our planet's weather. And once you know what you're looking for, you see this engine everywhere. You know when you're boiling water and you see it rolling around in the pot? That's a convection current. A space heater warming up a cold room? It's creating a big loop of rising hot air and sinking cold air. That lovely breeze that cools you down on a hot day? Yep, that's convection too, as the air flows past and carries heat away from your skin. On a huge scale, this is what drives ocean currents and builds those massive thunderhead clouds. Okay, time for our third and final path, radiation. And this is the one that's a little bit mind-bending. This is how heat can travel across incredible distances, even through the complete emptiness of space, something that conduction and convection just can't do. So what makes radiation so special? It needs absolutely nothing to travel through. No air, no water, no solid material. It's not about molecules bumping or flowing. We're talking about pure energy shooting through space in the form of electromagnetic waves, things like infrared heat, or even the light you can see. The wild part is, basically any object that has a temperature above absolute zero is constantly blasting out these waves. And the ultimate example of this, of course, is the sun. Think about it. It's warming our entire planet from 93 million miles away across the total vacuum of space. There's nothing connecting us for conduction, and there's no air or water for convection. Every bit of that warmth, all that energy that makes life possible, gets here as radiation. But here's a cool thing. How an object deals with this radiation really depends on its surface. Dark, rough surfaces are great at both soaking up radiation and spitting it back out. It's why a black t-shirt or black asphalt gets so blazing hot in the summer sun. On the flip side, light-colored or shiny, mirror-like surfaces are terrible at absorbing radiation. They just reflect most of it away. And because they're bad at absorbing, they're also bad at emitting. Okay, but now, this is where radiation gets really, really wild. The connection between an object's temperature and how much heat it radiates, it isn't a simple one-to-one relationship. It's an explosion. The amount of heat it gives off is proportional to its temperature to the fourth power. So what in the world does 2 to the fourth power even mean? Well, it means this relationship is incredibly strong. If you double an object's temperature, you don't just get double the radiated heat. No, you get 16 times as much. This is why you can feel the heat from a bonfire from so far away, and it's why even a tiny change in a star's temperature can make it seem massively brighter to us here on Earth. Okay, so let's recap. We have our 3 paths: conduction by touch, convection by flow, and radiation by invisible waves. So now, let's put them all together and see how these ideas are used in things we see every day and how they literally shape our entire world. Let's start with something simple, like a thermos flask. A thermos is basically a little fortress built to stop heat transfer. How does it do it? Well, it's got that vacuum between the inner and outer walls. That vacuum stops conduction and convection right in their tracks, because there's no air or matter to move the heat. And that shiny silver coating on the inside, that's there to defeat radiation by reflecting all the heat waves right back where they came from. It's an amazing piece of engineering that tackles all 3 paths. Okay, that's a small scale. Now let's scale that thinking way, way up, from a thermos to the entire planet. Because these exact same principles are at play in our atmosphere, driving a process you've definitely heard of, the greenhouse effect. So here's how it works. Our planet soaks up all this energy from the sun, and then it radiates that heat back out toward space. But some of the gases in our atmosphere act like a blanket. They trap some of that outgoing heat and radiate it back down, keeping us warm. And the impact is just massive. Without this natural greenhouse effect, the average temperature on Earth would be about 40 degrees Celsius colder, basically a giant ice ball. So you see, from that first shock of a cold tile floor in the morning to the feeling of a cool breeze, all the way to the warmth of the sun on your face, these 3 secret paths of heat are constantly working behind the scenes. They shape our daily comfort, they drive our technology, and they define the climate of our entire world.
And now that you know the rules of the game, you're going to see it everywhere. You'll see conduction, convection, and radiation in the way your jacket keeps you warm, in how your oven cooks your food, and in the weather report on the news. They've been there all along. The only question now is, what are you going to notice first?